Hi, I'm Professor Goins. In this video, I'm going to look at the concept of a surface integral. So by a surface integral, what I mean is I'm looking at this double integral where the region of integration S is some sort of a surface in 3 space. And what we want to do is figure out how can we compute this. Now keep in mind that if the surface lies on in 3 space is this curved region, the differential is going to be d sigma, where d sigma is actually going to be a little patch on that surface. And it's an infinitesimal curved piece. So what I'm going to do is figure out how can I convert this to a double integral that we can evaluate. And here's our procedure. I'm going to convert the integral as follows. So what I have to do is I have to convert 3 different parts of this: the region of integration, the integrand, and the differential. So let's see what happens here. I'm going to convert the region of integration S to D. So the curved surface in 3 space, I'm going to look at the projection of that onto the XY plane, which is going to be this region in 2 dimensions. So it's going to be this plane region. So S gets projected down to its shadow. I'm going to replace the variable z in the integrand. That's going to get replaced by the equation of the surface. So z is going to get replaced with g of xy. Now for the differential, if I can consider this piece on the surface, so this differential curved piece, I'm going to project it down to a plane differential, so an area differential in 2 dimensions. But there's going to be some sort of a conversion factor. It's not just d sigma gets replaced with dA. So let's figure out what this conversion factor would be. And to do that, let's go back to that surface. Let's look at the surface again. And what I'm going to do is I'm going to put a variety of patches on here, and I'm going to project those down to a variety of patches here. Okay, so we'll come back to that here in a second. The surface area of this. So the surface area is given by the double integral over this region D of the square root of 1 plus the square of the partial of z with respect to x plus the square of the partial of z with respect to y, and then we integrate that where the differential is dA. And remember, dA represents either dx dy or dy dx, depending on which way how the region D is represented. But this was the surface area integral that we covered in another video. Now what I want to do is let's interpret this. The surface area, if I was to consider take this thing and decompose it into surface patches, the surface area is just the sum of all those patches, the sum of all those surface area patches. So the surface area is the sum of all the surface area patches. If I project all those down into this plane region, then this double integral is over this region here, and I'm taking the sum of all of those patches with this correction factor. Since I'm taking a curved region to a flat region, we have this correction factor. And so the double integral on the right-hand side is the sum of all the plane patches with the correction factors. Now suppose my surface was really, really simple and consisted of a single patch. So rather than taking a sum of all these patches, I have a surface that has a single patch here. Well, then there'd be a single patch down here. That means that the d sigma, which would be the sum of the patches, there's just one of them, so one patch would be equal to an area patch in 2 dimensions multiplied by the correction factor. So this right here is how I convert a surface area differential to a plane differential. Okay. So let's go through and let's compute an example of a surface integral. so for my surface, I'm going to use the portion of x squared plus, or z squared plus x squared is equal to 4, which would be the cylinder of radius 2 centered on the y-axis, right? It's independent of y, so it'd be z squared plus x squared equals 4. Think of that as a circle of radius 2 in the xz plane, and then y is independent, so it'd be that stack of circles, which again is equivalent to a cylinder. I'm going to take the portion of that in the first octant, and it's going to be bounded by, well, of course, we'll take x is going to go from 0 to 2, so it's going to have that entire portion of the cylinder, so x is going to go 0 to 2, and let's say y is going to go from 0 to 3. Okay, so the sketch of that region then would look like the following. X-axis, y-axis, z-axis. X goes from 0 to 2, so that means this point right here, the intersection of the cylinder and the x-axis occurs when x is 2. And I'm taking the cylinder from y equal to 0 out to y equal to 3, so this point right here would be y is equal to 3. Okay. So there's the surface that I want to take a look at, and here's the integral that I want to compute. Let's evaluate the double integral over that surface S of x, y, z, d sigma. Just like when we went through the generic description of what a surface integral was, we have to convert all three parts of this integral. I have to convert from the surface, this portion of the cylinder, down to a plane region. I have to rewrite the integrand so that it has only x's and y's in it, right? If it's a double integral, it can have at most 2 variables, and as far as getting a value for it. And then d sigma, I have to convert that to, so that's on the board here, I have to convert that to a plane area differential. Okay, so let's go through and see what this is going to look like. If I take that surface S, again this is the surface S, we find the region D by projecting that down to the XY plane. And if I project that down, you see that my region is going to consist of that rectangle. So my limits of integration would go, x goes 0 to 2, and y is going to go from 0 to 3. All right, and then the integrand z is going to get replaced by the equation of the surface. So z squared plus x squared is equal to 4. So that's going to give me if I solve that for z, we get z is going to be the square root of 4 minus x squared. And in case you're wondering, when I took the square root there, we get a plus or a minus, of course, but I'm only going to take the positive because we restricted our surface to lie above the xy plane, meaning z is not negative. So therefore, the integrand is going to be x, y, and then times this in place of z, and then my differential is going to get replaced by that expression down at the bottom. So here's the integral that we're going to compute. We're going to look at the integral from 0 to 2, integral from 0 to 3 of x, y, square root of 4 minus x squared, so there's my x, y, z, and then for my d sigma, that's going to be the square root of 1 plus, so it's the partial derivative